See, what are the terms you need to know from thermo? Check it out. 1 second. 1 second. एक minute. You can see the screen.
No, sir, it's black.
It's black ones. First thing you must learn is what is system, surrounding, and boundary. System can be three types: open system, where there is no where there is an exchange of mass and energy; closed system, no exchange of mass but exchange of energy; isolated system, no exchange of mass and energy. There are two types of boundaries: diathermic and adiabatic. Diathermic is which conducts the heat; adiabatic resists the heat. Uh, we have two types of properties: extensive and intensive property. Properties like volume, mass, free energy, entropy, enthalpy, internal energy. All of these are extensive properties. And intensive properties are the ones which are independent of the content or independent of the mass. That includes molar volume, density, molarity, normality, molality, mole fraction, refractive index, viscosity, and molar change of free energy or entropy, and all of them in the molar form. And
Hmm.
then molar heat capacity, right? And this one is molar heat. This one is specific heat capacity, pressure and temperature. Extensive are usually additive, intensive are not additive. Okay. And you know that extensive, if you multiply that with extensive, you will get an extensive part. But extensive, when you divide by extensive, you will get an intensive part.
Hmm.
Okay. Now, electrode potential is one such case where you know that they are intensive in nature. They are not extensive in nature. So we directly cannot add the electrode potentials. We usually add their delta G values, which means energies. Okay. Next. What is a state variable? Anything which is independent of path is called as state variable. To verify the state variable, we generally do three things. First, if phi is a state function, then integral a to b, and as you integrate d phi, it will always become phi b minus phi a. So irrespective of how the function is, it will always be the value, the difference between the difference between these 2 points. And again, integral of d phi will be always equal to 0, cyclic integral, which means uh, just a second. So we can make a cyclic uh, derivative or cyclic integration of d phi is equal to 0. That means it is a state function. Another way to use is Euler's equation or Euler's theorem, where you differentiate the psi with respect to one variable and then you differentiate that with the second variable. And those two variables can be interchanged and yet you'll get the same result. For example, pressure is nRT by V. If you differentiate that with respect to V, I'll get minus nRT by V square. While if you differentiate with T again, I'll get minus nR by V square. But if you differentiate that with first with T, you will get nR by V. And that if you differentiate by dV minus nR by V square, you can see the result is the same. Hence, we can say uh, pressure is a state function.
Hmm.
Another way to look into it is you should be able to write the exact differentiable function. That means if internal energy is state function, it should be able to represent that in terms of temperature and volume. That is du is equal to du by dv at constant temperature into dv plus du by dt at constant volume into dt. This is a way we should be able to represent. In fact, if you have a state function c and it is with in terms of a function a and b, then this is the way we can write it down. Okay, this way if you are able to write anything, this is called as state function. Path functions work and heat, which depends on path. I'm sure you are aware of it. We use the word thermodynamic equilibrium when there is thermal, chemical, and mechanical equilibrium all are present in the system. What are the types of processes? Isobaric process, where you have delta P is equal to 0. Isochoric process, delta V is equal to 0. Isothermal is delta T 0. Adiabatic is Q is equal to 0. Well, you see, the energy conservation in a closed system is what we refer as the first law of thermodynamics. Delta U, that is any change in internal energy, is a result of heat and work. Okay.
Hmm.
And you see, conventionally, anything out of the system is always negative and anything to the system is always positive. So, if at all it is been given, work done is by the system, that means it is less than zero. Heat is given to the system, positive. Heat is taken out of the system, negative. Okay.
Hmm.
Next, internal energy. Because it is a state function, the cyclic integral of du is zero. And du can be written in terms of exact function or exact differential. And you know that du is basically, internal energy is basically the sum of all the types of energies present in a system. There are mainly two types of energies which will be present, kinetic energy and potential energy. So sum of all those energies will give you, internal energy. This is U. Okay. Next.
Yes.
For an ideal gas, because there is no change in potential energy, you know that change in potential energy for an ideal gas is zero. And kinetic
Yeah.
energy of an ideal gas per particle is 3 by 2 kT, or average kinetic energy of particles is equal to 3 by 2 RT for 1 mole.
Hmm.
So therefore, any change in the internal energy, because there is no kinetic energy change, we can say only there is no potential energy change. We can say only kinetic energy is changing. So kinetic energy change can be written as 3 by 2 R into delta T. So we can say internal energy is a function of temperature. Okay.
Yes.
For instance, if you notice for real gases, P plus A by V square V minus V is equal to RT is the van der Waals real gas equation. Pressure can be written in this format, isn't it?
Hmm.
And du is equal to dq plus dw, and dw is equal to minus pdv.
PDV.
Okay. Okay. So and at dv is equal to 0, dw is equal to 0. Correct.
Yeah.
So dq at constant volume will be equal to du. Okay.
Huh.
This is at constant volume. Now heat
Yes.
capacity, how do we define it? Heat capacity is dq by dt. That is heat given to change the temperature by 1 unit. That is called heat capacity.
Yeah.
Now, if I say that the same heat capacity as molar heat capacity, then you have to divide it by number of moles. Okay.
Yeah.
And we say molar heat capacity at constant volume, then that
Hmm.
means the heat supplied should also be at constant volume.
Okay.
So therefore, dQV is equal to du, which is equal to NCV dt.
Hmm.
And if I bring this dt to the denominator, I'll get this as NCV. Okay, so du is equal to du by dt into dv plus du by dt into v dt, correct? This is how
Yeah.
the exact function we can write it. And now you notice that du by dt can be written as NCV. So we can write it as NCV dt. So basically, I would suggest you remember the equation more in this format. Okay, this will be
Yeah.
more useful format. Du is equal to dou u by dou v into dv plus NCV dt. Okay. Now,
Yes.
here is the interesting part. There is something called equation of a state, which you have to directly remember that any change in the internal energy with respect to volume can be written in terms of temperature multiplied by dp by dt minus P. Okay.
Hmm.
Now, P is this value, correct? Now, differentiate that with respect to V. So, what would I get? Sorry, differentiate with respect to T at constant temperature. This value will be 0 and this will become R by V minus B. And multiply that with temperature again. Here you can see temperature again. So, RT by V minus B. Got it?
So,
And
yeah.
then what is the equation of a state? Du by dv is equal to dp by dt, correct? So du by dv is equal to this entire thing we found out to be RT by V minus B. And P value, you know that this is the one. I'm substituting
Yeah.
that. So you can see these two will get cancelled. You will get A by V square. So the same equation here for a real gas, turns out to be this way. Du is equal to A by V square into dV NCV dt. Okay.
Hmm.
So if I integrate that, I'll get delta U is equal to A into 1 by V1 minus V2 plus NC T2 minus T1. Okay.
Yeah.
This is how you'll work out for the real gases. Okay. Enthalpy of a system refers to the overall heat content of the system, which means if I take H, that is equal to U plus PV. U, I can also write it as E, which is internal energy plus PV. If at all I try to differentiate that, I'll get dH is equal to du plus PdV plus VdP. And
Yeah.
at constant pressure, dH is equal to this value will become 0. So du plus PdV. Okay. And if you recall from first law of thermodynamics, dq is equal to du minus dw
Yes.
and du and the dw can be written as plus PdV.
PDB.
Correct. So dH is equal to NCV dt plus PdV. Okay, because du I know that I can write it as NCV dt for ideal gases. Okay,
Yeah.
and it appears like this equation and this equation is same. Correct.
Yes.
So therefore I can write dH is equal to dP at constant pressure. Okay. So therefore, heat capacity at constant pressure can be defined as dQp
DQP.
by ndt. And dq is equal to ncp into dt and dq is equal to dh at constant pressure. Okay.
Yes. So CP by C. Okay.
Yeah. So now I can write delta this equation, which is delta H is equal to delta U plus P delta V. That can be written as Cp minus Cv is equal to R. देखो P delta V can be written as NR delta T. So I have used that value. Hmm.
Yeah.
And Cp by Cv is called as gamma. And Cv can be written as total degree of freedoms into R by 2. Okay. Now degree of freedoms is basically number of dimensions a particle can move freely. Okay.
Yes.
So you notice that if a particle is moving and it is just a spherical particle, a small spherical particle moving in space, that means it is moving in X, Y, and Z direction. So those kind of dimensions which are defining the position of a particle, that is known as translational degree of freedoms.
Yeah.
So if a particle is moving from point A to point B, you will have three translational degree of freedoms. Okay. Then rotational degree of freedoms, depending upon whether the particle is linear, whether it is spherical, or whether it is non-linear. Suppose if a molecule is, linear like this, okay, and this molecule is going from A to B, then its rotation in one direction can be ignored, but rotation in other two direction cannot be ignored. For example, if we have a particle here, correct, with respect to this axis, it can rotate if it is linear, correct? Understood? The
Yeah.
particle with this axis can rotate. If it is like this, it can rotate in this axis also. Here, but
Yes.
a particle cannot rotate in this axis. I mean, it will rotate, but its contribution will be minimal,
Yes. Okay.
correct? So this is the part which we are ignoring. So let's say we ignore that. The other two directions, we will have a contribution of rotation.
Yeah.
Vibrational degree of freedoms is always, given as a formula as 3n. 3n is the total degree of freedoms possible minus translational plus rotational. Okay. N represents number of atoms present in the molecule. Suppose it is H2, then N is equal to 2. Total translational degree of freedoms are 3. Rotational is 2 because H2 is linear. So rotational will be 2. So vibrational will be 6 minus 5, which is 1. Suppose if
Yeah.
I take for methane, the maximum degree of freedoms is 3n, which is 3 into 5, 15. Out of which there are 3 translational, there are 3 rotational because CH4 is non-linear,
Yeah.
non-planar. So definitely you cannot ignore anything. All the contributions of rotation will be observed. And vibrational degree of freedoms will be 3n minus 6. So 15 minus 6 is 9. Okay, beta?
Yeah.
Right. You know that at room temperature, if you want to find out the degree of freedoms of methane, you'll find the total degree of freedoms are 6. Okay. And at high temperature, we assume all the degree of freedoms are active. That means even the vibrational is active. So the total degree of freedoms will be 15. Okay.
Hmm.
If I want to calculate the CP and CV at room temperature, okay, first I will notice that du is equal to 3 by T, 3 by 2 nr delta T, correct? Because it is equal to change in kinetic energy. And that is equal to ncv dt. So you can see nn will get cancelled, dt is getting cancelled. So cv is equal to 3 by 2 r. If it is, you have 3 by 2 r here. So 3 by 2 r can be written as r by 2, r by 2 plus r by 2. So that is equipartition of energy. Okay.
Hmm.
And you see, every translational degree of freedom is equal to r by 2. Every rotational degree of freedom is r by 2. Every vibrational degree of freedom is r
R.
contribution.
Yes.
It is not r by 2, it is r contribution.
Yeah.
So CV at H2 will be equal to 5 into r by 2, correct? Because you know
Yes.
that 3 of translational and 2 of rotational, that will be active.
Yeah.
So 5 r by 2. At high temperature, 5 r by 2 plus 1 r
R.
due to rotation. So therefore 7
Yes.
r by 2. And CV of CH4 at room temperature is equal to 6 r by 2 because 3 translational, 3 rotational are present. So that is 6 r by 2. And next, CV of methane at high temperature will be 6 r by 2 plus 9 r. 9 r is the remaining amount of vibrational degree of freedoms, which is 12 r. Okay.
Yeah.
So if you notice, we will always be using this for CV and CP value and gamma. For monoatomic, it is 3 by 2 r. Diatomic 5 r by 2 or 5 by 2 r. And polyatomic or non-linear, it is 3 r. CP will be, because CP will be CV plus R. So you have to just
Yeah.
add one R here and R
Yeah.
here. You will get the respective values.
Yes.
Gamma will be 5 by 3, 7 by 5 and 4 by 3.
Yeah.
So you can notice that as the complexity in the molecule increases, the gamma value decreases. Okay.
Yes.
See, if you're moving, the piston kind of a function in a system from a point A to point B in one shot, I mean,
Hmm.
instantly, right? Then that is called irreversible change. If you are going very gradually, very slow, and taking one step at a time, like this, one step at a time,
Yeah.
then having infinite step makes it reversible. Okay.
Yes.
So imagine if internal pressure is more than external pressure, then we say expansion is happening. If external is greater than internal, we say compression is happening. Okay. And
Hmm.
if these values are sufficient difference, that means there is significant difference between these two
Yeah.
pressures, then we say an irreversible work is happening because there will be always sudden movement. But if the internal and external pressures are very, very close, there is an extremely small change, then we say the expansion or compression is reversible work. Okay.
Yeah.
Now notice, if it is a reversible work, the work done formula is a generic formula which is minus integral V1 to V2 P external into dV. Okay, that is P external into dV. So
Yeah.
P external can be written as P internal into dV. Okay,
Mm.
for a reversible process. So P internal can be written as nRT, into dV, nRT by V into dV. So nRT by V, if you integrate that, we will get this as minus nRT ln V2 by V. Okay. So this is what is reversible work done. du is
Mm.
0, which means delta U
Yes.
is equal to 0. Q is equal to minus W of reversible, correct?
Yeah.
So Q will be, the minus sign will become plus sign, plus nRT ln V2 by V. Suppose if
Mm.
you started with a point A here and reaching towards point B here, correct? And at point
Mm.
A, we have P1, V1 as the pressure and volume term, and P, we have P2, V2. So from here to here, as you come across the amount of work done in this here, that is called
Mm.
the uh, reversible work done here. Okay.
Yes.
And next, you see what is irreversible work done. So work is equal to minus integral V1 to V2 P external into dV. So minus P external V2 minus V1, if you compare, here P external is not equal to P internal. But one thing is for sure, suppose if you're going from this point to this point, that is A to B, but this time you are going irreversible. For irreversible, there is no graph. But I know that irreversible always ends at a point where the pressure becomes equal. So that means the final pressure of the gas will be always equal to external pressure. So this is the external pressure. That external pressure into change in volume is what is irreversible work done. So that is area under
Yeah.
this graph. Clear?
Yeah.
So you can see from the graph itself, that is work done. If it is work done in a reversible system for an expansion of an isothermal process, magnitude is greater than work done in an irreversible process for same expansion for isothermal process. Correct?
Yeah.
Based on these two graphs, area. Similarly, in the case of compression, what will happen? From this point, P1, V1, you are going all the way to P2, V2, this way. So area under the curve will be same. That is how much isothermal expansion has been done. Same is the isothermal compression. But if it is irreversible, you started with this point, you reach to this point. There is no graph, but final pressure is equal to the external pressure. So this is final pressure, and multiplied by the difference in the volume here, that makes that covers the area under this graph, which is irreversible work. Okay.
Yeah.
So you can see reversible expansion is equal to reversible compression, but reversible expansion is greater than irreversible expansion, while reversible compression is less than irreversible compression. You can see irreversible area is more than reversible area in this case. Okay. Suppose if
Yeah.
you notice a cyclic case, from B to C, this is the area that is covered, correct? And
Yeah.
D to A, this is the area that is covered. Okay. So the resultant will be this one minus this one. Okay. So what is left? This
Yes.
one is left. So therefore, the overall work done from A to B, B to C, C to D, and D to A here will be simply area under the graph. And since if it is moving clockwise, the overall work done is going to be system. Got it? Work done is by the system, right? So therefore, it is negative value. Okay.
Yeah.
So remember, clockwise cycle is negative, anti-clockwise cycle is positive work done.
Yes.
Okay.
Yes.
Next, if it is delta H of isothermal or delta H of delta U of isothermal for a non-reacting gas. Since the temperature is not changing, these values will be zero. Okay, beta.
Yeah.
Now, let's see about adiabatic process. If we talk about reversible adiabatic process, so that is Q equal to zero, then dW is equal to dQ, which is equal to NCV dt, which is minus PdV. That can be written as minus nRT by V. Okay.
Yeah.
Now, if I equate these two, Cv by RT into dt is equal to 1 by V dV, correct? So, because this I'm equating with this one, so that n will get cancelled. These are the values you will have. Now, integrate them on both sides. So, you will get this as T2 V2 power gamma minus 1 is equal to T1 V1 power gamma minus 1, which is equal to constant. Similarly, PV raised to power of gamma is constant. T raised to power of gamma into T raised to power of 1 minus gamma is constant. These equations are only valid for reversible adiabatic. Okay.
Yes.
So this is how it should be mentioned. A reversible adiabatic process is undergoing expansion from T1 at a volume 2 liters to 64 liters. Find the work done and change in internal energy. In such
Yeah.
case, you first calculate the T2 value. T2 value is T1 into V1 by V2 into gamma minus 1. So gamma
Yeah.
is given. It is uh, this one, a diatomic gas. So you can see. Since it is a diatomic gas, gamma will be equal to 7R by 2 divided by 5R by 2. So that is 1.4. Okay. So or simply
Yeah.
I can write it as 7 by 5. Correct. So 7 by 5 minus 1 is equal to 2 by 5.
Hmm.
And that is equal to 300 into, as you work it out, you will get this as 75 kelvins. Now I know the change in, I know the final temperature in and initial temperature. I can calculate delta U, which is equal to NCV delta T. And since it is an adiabatic process, Q is 0, so W is equal to delta U. Yeah?
Hmm.
Typically, this is how you find out the work done in reversible case. Now, on a similar basis, this time if it is irreversible case, see, I have a monoatomic gas expanding adiabatically from this point 10 atm to 5 liters to 5 atm 10 liters. Find the final temperature, work done, delta U, delta H starting from temperature 27 degrees. Okay.
Yeah.
So you can see delta U is equal to W. Delta U can be written as NCV delta T, and work done can be minus P external into uh, delta V. So
Yeah.
this NCV delta T is equal to minus P external into 10 minus 5. So as you substitute all of these values, you know that final pressure will always be equal to, external pressure is always equal to final pressure.
Yes.
Using that, I can calculate what is T2. That is the only part which is unknown. Okay.
Hmm.
I hope this part is clear. So once you get
Yes.
the temperature, you can calculate delta U and delta W because Q is 0.
Oh, okay.
Right. Majority of the questions from first law will be based on adiabatic only. So you got to understand these two concepts, how it varies for reversible and irreversible.
Hmm.
Next, check out entropy change of an ideal gas. Right, ds is equal to dq by t. For an ideal gas, ds is equal to ncv, 1 by t dt. Clear? Because ncv dt is heat, this one, and divided by t. So that is divided by t. That
Hmm.
plus, and q reversible can be written as nr 1 by v dv, because dq can be written as du plus du minus tw, and du can be written as ncv dt, and this can be written as plus pdv. Understood now? And plus
Ah.
pdv can be written, p can be written as nrt by v. Okay, clear?
Yes.
So if I divide it by t and t, so I can write this one nc by v. Here I have written nc by v. Clear? This is NC by V. And P by T can be written as NR by V. Okay.
Yes.
So that's how I equate for ideal gas. So then on integrating, I will get the value as NCV ln T2 plus T1 and NR ln V2 by V1. Okay. And you see for isothermal process, delta S of the system is equal to NR ln V2 by V1. Hmm. And the same for isochoric process will be delta S is equal to NCV ln T2 by T1. Okay.
Yeah.
This is for uh, a thermal process and this is for isochoric process. Clear?
Hmm.
Next. You see a system is isochorically expanding from its temperature 127 degrees to 27 degrees. It is said to be reversibly expanding. Once it is said it is irreversibly expanding, losing 800 joules of energy to the surroundings. And once it is making a free expansion. So using these fundamentals, we need to figure out what happens to delta S of the system, delta S of the surrounding, and delta S total.
Hmm.
See, delta S system is this formula, right? Because it is first one isochoric, so the volume is constant. So this volume factor does not come into picture. Okay. So we have NCV T2 by T1. Clear,
Yeah.
beta? Any doubt here?
No, sir.
Right. So we have one more, and CV is 3 by 2 R ln T2 by T1. Okay. So this is T2 and this is T1 127. And you know that if it is reversible, for a reversible delta S system and delta S surrounding will be same just by negative value. Okay. And delta S total will be sum of these two, which is equal to 0. Got it?
Uh,
This is first case. Now see second case with irreversible form. So delta S of system, as long as the final temperatures are same, so the value will be same because these are state functions. Whether you make a reversible change or an irreversible change, the change should be same. So delta S of the system change should be same. But delta S of surrounding is not equal to system. Now, delta S of surrounding will be Q reversible by T. So as per question, it is said that you know that irreversible will be equal to T delta S of the system, right? But that
hmm.
minus 800 because he said 800 is lost to the surroundings. So T delta S of the system minus 800, that will be the total heat that is been received by the system.
Yeah.
Okay, beta? So substituting this value here, I'll get Q irreversible. Now, how do I calculate delta S of the surrounding? ये आ गया ना? Q irreversible by T. Clear?
Uh,
So this you can write down. Just one thing you need to understand. ds of the system is not equal to dq irreversible by T. But ds of the surrounding will be always equal to minus dq irreversible by T. Just keep this in mind. Okay.
yeah.
So that formula is not valid for system, but the formula is valid for surroundings. That's why
Hmm.
I've written that minus q irreversible by T. Okay.
Yeah.
So now if you substitute all of that, you'll get delta S of the system plus delta S of the surrounding, and it has to be greater than zero. Then only we say it is favorable as a thermodynamic second law. Okay.
Uh,
See, if work is zero, delta V is greater than zero, delta T will be equal to zero. Okay. So delta S
yes.
of the system is equal to NR ln V2 by V1, which is greater than zero. Delta S of surrounding is minus Q irreversible by T, which is equal to zero. So delta S total will be greater than zero. Okay.
Yeah.
See, for an adiabatic irreversible process, Q reversible is zero. If Q reversible is zero, delta S of the system, whose formula is dq reversible by T, this will also become zero.
Yeah.
If system is zero, surrounding will be zero. If surrounding
Yes.
is zero, the sum of these two will be zero. Such a type of process where entropy of system surrounding always remains constant, that is called isentropic process. So remember, reversible adiabatic process is called as isentropic process.
Yeah.
Okay. If it is adiabatic irreversible process, Q irreversible is 0, delta S of system is greater than 0, delta S of surrounding is equal to 0, and delta S of total is greater than 0.
Uh,
Okay, clear beta?
yes.
Next, if you have two metal blocks connected with each other and both of them are at two different temperature and they have different masses, then the total change of entropy of both the metal blocks together is change in delta A plus change in delta B.
B.
I
Yes.
mean entropy of B. Change in entropy of A will be equal to M1 C L1 T2 by T1. Okay.
Yeah.
And delta SB will be equal to M2 C ln TF by T2. So this is TF by T1, this is TF by T2. What is T final? T final is always going to be the weighted average. The weighted average will be equal to M1 T1 plus M2 T2 by M1 plus M2. Correct? So
Yes.
T1 to this temperature it is changing. B is T2 to this temperature it is changing. So you got to put these as the final temperatures while solving. Okay?
Yeah.
Next. In case if you have H2O, it is in equilibrium with H2O liquid. And let's say I have 5 atm pressure here and 2 atm pressure. Temperature is minus 10 degrees and here temperature is 10 degrees. In such physical cases, how do we calculate the entropy change? So what you do, the solid which is at minus 10, first you bring it to 0 degrees. Okay.
Yeah.
So here there is an entropy change. So how do we address that? NC T2 by T1. What is the C value for this change? It will be given. That means what is the heat capacity of a solid that will be given to you.
Hmm.
And then from solid at 0 degrees, you convert that into liquid at 0 degrees. Because this is an equilibrium form, delta G will be 0 and delta S will be equal to delta H by T. Because you know that delta G is equal to delta H minus T delta S, correct? So if
Yeah.
this is 0, so delta S will be equal to delta H by T. Okay?
Yeah.
And from then you make this from 0 to 10 degrees. So 0 to 10 degrees, again delta S will be NC ln T2 by T1. So sum
Yes.
of these three will give you the total entropy change. Okay.
Hmm.
One second. You can see this example. For a physical equilibrium cases from minus 10 degrees to 200, how I have written it. Okay. Minus 10 to 0. This is the value MS ln this one. 0 to 0, delta H of fusion by 273. Then 0 to 100 degrees, again delta S NC ln 373 by 273. Again for 100 to 100 with liquid to gas, it is vaporization by 373. And from 100 to 200, it will be NCV ln T2 by T1. Okay.
Yeah.
Right. Next, let's talk about third law of thermodynamics. See, at 0 kelvins, entropy of a perfectly crystalline substance is 0. That is S of T minus S of O is equal to integral 0 to T Q reversible by T. Okay.
Yeah.
And see, S at 0 kelvins is equal to 0. For a perfect crystal, it is 0. Then S total will be equal to integral 0 to T Q reversible by T. Q reversible can be written as Cp dt by T. Okay. At
Yes.
a constant pressure, this can be written as Cp dt by T. If there is an entropy change thereafter, I can write T1 to T2 Q reversible by T or T1 to T2 Cp dt by T. For example, just now we learned that entropy changes happen from 1 to 2 here, then solid to liquid change, then liquid to gaseous change, and gaseous to gaseous. Okay.
Yeah.
So these are the values 1 to 2 Cp by delta T, 2 to 3 sudden change delta H of fusion by T, 3 to 4 Cp delta T by T, and 4 to 5 delta H of vaporization by T, correct? And 5 to 6 Cp dt by T. This is how you calculate for this one. Okay. Now, in general, you remember entropy of gases is way higher than liquids than solids.
Yeah.
So, aqueous solution will have more entropy than a pure liquid. Aqueous solution of salt compared to that of solid, obviously aqueous is more. Iodine, bromine, chlorine, fluorine, if you compare, more the molar mass, more is the entropy. Okay.
Yeah.
You usually have more entropy. Next, graphite entropy is more than diamond. White tin is greater than that of gray tin. And if you compare all of these, metals and non-metals, mercury will have the highest entropy in its natural form, then lead, then silica, then beryllium, and then diamond. Okay.
Hmm.
AlCl3 will have more covalent character. That's why it has more entropy than MgCl2. NaCl is highly ionic character. Okay.
Yeah.
And as the X increases, entropy will also increase in the case of copper sulfate dot this one. Okay. Next, see what is the spontaneity of the reaction? Delta G at constant temperature and pressure can be written as minus T delta S of the total. Okay.
Yes.
So again, I'm not getting into the derivation directly. You should remember this. Okay.
Ah.
And delta, if a process is spontaneous, then we say delta S total should be greater than zero.
Yes.
If this is greater than zero, delta S of the system should be less than zero. And delta S of system can be written as delta H of the system minus T delta S of the system. And see, delta H we have different values, delta S we have different values. At different temperatures, what will happen? Check out from the equation. If this is positive, positive, and at increasing temperature, you know, delta S
Hmm.
will become negative. So that means it is spontaneous at high temperature. If delta H is positive, delta S is positive, and temperature is low, so delta S is positive, that means it is non-spontaneous at low temperature.
Yeah.
Next, if delta H is negative, delta S is positive, it will, whether it is high temperature or low temperature, delta G is always negative. So that means it is always spontaneous. Similarly, if this is positive and this is negative, whether it is high or low temperature, delta G will be always greater than zero, so always non-spontaneous. Okay, clear? Second, see. So therefore, for these two cases, again, as the temperature increases, it is non-spontaneous. As it decreases, it is spontaneous. Next, just like entropy, if you compare the free energy of the gases is, more than liquids than solids. Okay. And
Yeah.
usually at low temperature, this is what you'll observe. And at high temperature, solids will be greater than liquids than gases. Okay.
Yes.
Delta G is equal to 0 for a reversible reaction, and general equation for delta G is delta G naught plus RT ln Q. And for a reversible change, delta G is equal to 0 and delta G naught is equal to minus RT ln K equilibrium, right? So I can write it as minus RT ln K. Well, delta G naught can also be expressed as delta H naught minus T delta S naught, which is equal to minus RT ln Kp. So if I bring this RT to the left hand side, I will be able to get this equation, which is ln Kp ln Kp versus 1 by T can be written as a equation of a straight line.
Ah. Yes.
And positive slope if delta H is greater than 0, less than 0. Negative slope if delta H is greater than 0. Okay. At two
Yes.
different temperatures, if I write this equation, then add them, I will get this as the Van 't Hoff's equation. So this is Van 't Hoff's equation. Clear, beta?
Yeah.
Okay. Right. So this is